scientists are shaping the future. My name is Professor Martin Thuo, and my name is Professor Martin Thuo, coming to you from the Eastern Seaboard of the United States in North Carolina State University. Today, we're going to be hearing from three very talented rising stars, starting with Professor Fujii, Professor Shu, and Professor Qin. And the panel will consist of myself and Alice and Zhang. Our first speaker today is going to be talking to us about characterization and application of laser-induced microbubbles. Professor Fujii has a very long and detailed bio, so I'm going to just go through the highlight. He is an associate professor in the Department of Natural Sciences at the National Institute of Technology at Kisarazu College in Japan. He got his PhD in applied chemistry from Chuo University in Tokyo in 2012 under Masaaki Haga. Then from there, he followed with a few postdoctoral studies, taking him around the world from Japan to Taiwan to Penn State, and then back to Tokyo University from 2021 to 2013. And then he in 2015, he joined the group of Professor Noboru Kitamaru and Professor Kosei Ueno at Hokkaido University as an assistant professor, where he stayed until 2021. And then he moved now to his current position. In 2024, he will be moving again to Yamagata University to lead the research group as a principal investigator. His research currently focuses on the interface chemistry of laser-induced microbubbles and its application, terahertz and sub-terahertz waves for non-destructive testing, electrochemical metal complex catalysis, among others. He's been awarded several awards. I'm not going to go to all of them. The one I want to highlight is the Incentive Prize Presentation Award of the Japanese Society of Applied Physics and the JSPS Hope Fellow in the 2012 meeting. So, Professor Fujii, the stage is yours.
Yes. Thank you, Martin. Let me share my slide. Can you see my slide?
Yep, looks good.
And okay. 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 Thank you, Martin, and for kind introduction, and also Alice and Martin. Thank you for arranging ICANX and giving me this opportunity. I'm honored to be here. My name is Fujii from National Institute of Technology at Kisarazu College. I would like to talk about the characterization and the application of laser-induced microbubble. First of all, let me share key information. What is a laser-induced microbubble? So irradiation of focused continuous wave laser on an interface between liquid and solid interface. And then hot thermal energy generates a single and small bubble. This is a laser-induced microbubble. So this bubble interface, also called three-phase contact line, provides solute concentration, accumulation, and chemical reaction. Before we get into the scientific content, let me introduce my college. So Kisarazu is located near Tokyo and about 30 minutes by car from Haneda Airport. This line shows the highway, and half of which pass under the sea, and the other half over the sea. So it's easy to access to the airport and Tokyo from our hometown. And this photo is an earlier view of our institute, COSEM. It is slightly larger than a high school. So this slide shows a brief introduction to the education system of COSEM. So after graduate school, junior high school, it is common for students to move up to the high school and then to college and university and graduate school. On the other hand, there are schools in Japan where students can receive practical engineering education after graduating from junior high school. So these are technical college. So this is COSEM. So, and the unique system is a 5-year engineering education system from 15 years old to foster top level practical and creative engineering. So various career paths are there. IT's basics subject and chemistry, and mostly to the students between the age of 16 and 18. So, okay, let's get back to the research. This is my outline talk. So, first, I will share my interest and motivation. And after that, introduce property of microbubbles about concentration and accumulation, and chemical reaction and material orientation using the bubble. Finally, I would like to summarize my talk. So I'm interested in the interfacial phenomena because also nanomaterial assembly, separation, and chemical reaction, adsorption, friction, and lubrication of materials are related to interfacial phenomena. Then I would like to understand the interfacial phenomena and develop smart chemistry. So this is my motivation. So in this talk, I focus on the material assembly, so nanomaterial assembly. So in particular, so nanomaterials such as nanoparticles and biomaterials and carbon materials and molecules, supermolecules, have attracted many researchers due to their unique properties. We use nanomaterials as a building block to produce something. And then bottom-up integration is required. So I believe that the key points to be noted in the process are manipulation, positioning, and orientation. For example, here shows the carbon nanotube-oriented arrays. The resistance of the array is so here. The resistance of array is smaller than that of random. So this means that oriented accumulation utilizes material properties. So the orientation is also one of the key points, I think. So what approach can we satisfy the 3 key points? So laser light is an attractive tool for space-time manipulation. So here is a famous report of single DNA molecule manipulation by optical tweezers, which has demonstrated that beads fixed at the both ends of the DNA are captured with optical tweezers, and string is noted. Another demonstration is optical manipulation and fixation of nanoparticles. So laser light can be as a guide for controlling the position of nanomaterial assembly. So our group also starts optical system. So shown here, so using neodymium laser 1060 nanometer, so injected into the inverted microscope, the behavior and the microscope was monitored by fluorescent image. And I made a liquid cell like this, and sample solution were injected into this space. Okay, let's move on to the first result we obtained. The first experiment was performed using DNA molecules. One end immobilized on the gold surface by gold cycle interaction and stained with fluorescent dye DNA. So this is a fluorescent microscope image of DNA. So usually DNA is shrinking, so this shape. So let me show the movie of response with laser irradiation. Here. So long distance interaction was confirmed with the distance between laser focal point and the DNA molecule being more than 20 micrometers. So this distance is beyond the potential range of laser trapping. So in general, potential range of optical trapping show interaction distance less than 1 micrometer. So what happened in our experiment? The answer is microbubble generated by laser local heating. So careful adjustment of illumination and the microscope provide the shadow of microbubbles. The size of the bubble depends on the intensity of laser light. So like this one, so 0 milliwatt laser irradiation is no bubble is shown, and 30 milliwatt and 50 milliwatt, 20 milliwatt. So the bubble is diameter is increased. So like this one. So lateral axis laser power and the vertical axis is diameter bubbles. And then we have applied the bubble property for materials assembly. So we have reported the bubble for manipulation, so DNA, so and stretching and pinning, and nanoparticles Q dot into ring like this one. So this is a solution behavior. So when laser irradiation on and Q dot into ring shape. And the next result is crystallization of glycine molecule like this one. So laser irradiation and molecule is accumulating, and then the nuclearization and crystallization is occurred. And so to briefly summarize the mechanism of this accumulation, so bubbles are generated by laser local heating like this. And then this bubble, laser local heating created by. So this bubble interface has a thermal gradient, and the thermal gradient gives rise to the gradient in surface tension, which causes convection. So this is Marangoni convection. So let's take a closer look at this space, like this space. The convection brings nanomaterials and molecule solutes into this space. So phenomena of concentration accumulation occurred here. So in addition, this bubble interface disappeared when stopping laser irradiation. And here's a question. So is this a specific phenomenon of the bubble? And the answer is no. There are similar phenomena around us. So that is, for example, tears of wine and coherent phenomena. So the unique feature of the bubble and interface, however, is that they can be controlled in space and time with laser. So now we would like to develop the bubble towards the next stage. So that means chemical reaction. So before introduction and concentration and accumulation, the next step is chemical reaction. So one demonstration is shown here. So Prussian blue is one of the most attractive functional materials for electrochromic and biosensor and fuel cell, battery, and magnetic material, and so on. One of the disadvantage is low solubility, so which is a difficult task in manufacturing in the solution process. Therefore, we attempt to synthesize Prussian blue only at the desired location using the bubble. So this is an experimental result. So the setup is the same result. It's the same before experiment setup. So after bubble scanning, so that means laser scanning, so stripe pattern were obtained. So this is FM image, and FM measurement revealed that the stripe pattern consists of the aggregation of nanorings. So this nanoring shapes about average is line width 1.2 micrometer, and average height is 150 nanometer, and inside ring diameter is 280 nanometer. So next, the stripe were measured by Raman spectroscopy, and the spectrum was similar to that of Prussian blue. This powder is a line signal and background ITO. So this peak is similar to the Prussian blue powder. So these results indicate that reduction reaction is proceeding. So for example, so first solution is this iron ion and this iron ion, and after bubble accumulation, the reduction reaction and provided Prussian blue. But this reaction mechanism is currently unknown. And next, another demonstration is chemical reaction at the bubble is shown here. So zinc oxide is also attractive functional materials for this application, like this. And previously, various methods have reported for patterning, like this, using PDM stamp and using zinc oxide nanoparticle. And after contact and move the mold and grows a nanowire. And another method is using polystyrene beads and remove this template and also growing up zinc oxide nanowires. So previously, various methods have reported for patterning. That through many steps. So then we tried bubble patterning. So experimental design is shown here, and this system is same and before I talked. And we scanned laser focused beam and in the solution phase, and using sample solution is 10 millimolar zinc solution. So this is one of the results. So 10 millimolar zinc solution at the pH 13. So laser scanning and provide the laser line, but so this line is disappeared. In contrast, pH 12, the laser scanning and line is still remained on the surface. So for the patterning, the key condition is pH. So pH 12 is best result. And after the pH check, and interestingly, a grid pattern shown here obtained by laser scanning. So, and this is a FM image, 3D image. So cross point is just overlapped the zinc oxide pattern. So here is showing the SEM and EDX data showing the deposit materials. And this EDX shown the deposit material, the zinc oxide. So like from this data and this data. And also XRD also supports the zinc oxide formation. And so like this small peak, so zinc oxide 002 is same peak at 34.5 degree. And also zinc oxide had, so compared to the previous report, zinc oxide had a preferred orientation with the Z-axis perpendicular to the surface. So we have so far confirmed the reduction reaction and hydrothermal synthesis phenomena and around the bubble, like this space. So finally, so here is an example of our effort to understand this space. So we want to understand the property of three-phase contact line, like here. So especially to obtain the information of temperature and pressure and orientation behavior in this small space. So how can we obtain the information? So then we try in this study observation of polystyrene beads behavior under the microscope with a high-speed camera. So the experiment setup is the same, and we use a polystyrene beads. Diameter is 0.5 micrometer. Glass transition temperature is about 100 degrees Celsius, and another particle is diameter is 0.2 micrometer. The glass transition temperature is 70 degrees Celsius, and we prepare another samples, the ellipsoidal polystyrene beads. So the abbreviation is EPB. So first, polystyrene beads is dispersed in PVA sheet, and then heat up and extend in the one direction. So we made ellipsoidal polystyrene beads. The first result is shown here, the accumulation of polystyrene bead SEM image. So the diameter of polystyrene beads is 0.5 micrometer is provided almost ring shape accumulation. In contrast, 0.2 micrometer polystyrene beads shown also provide the ring shape, but in the close view around here, polystyrene beads is a little bit melt and so contact. So in this result, we estimate the temperature heat up around this space is 70 degrees Celsius to 100 degrees Celsius. And finally, I calculated the fluid mechanics using this model. So this shows the glass surface on the between liquid solid interface, and this surface means the interface of bubble. And using this equation, so we solve the fluid mechanics. So to solve this equation, we refer this report, so support image bubble, and then we try to solve this equation and like this basis, and provided the analytical solution, and then summarize the bubble fluidic and image bubble fluidic, and summarize like this fluidic streamline. And then analyze using high-speed camera particle velocimetry and fitting this data. So we obtain the fundamental information that means that delta T, so the temperature gradient around this surface is 2 Kelvin. So this is just 2 Kelvin, but in the micro scale 2 Kelvin, the temperature gradient is 10 to 6 Kelvin per meter. And increasing pressure is around about 100 Pascal. So we succeeded to characterize this small space. And next, I tried to monitor the behavior of ellipsoidal polyethylene beads is shown here. The bubble attracts the particle, and the larger particle accumulate larger, like this one. In contrast, smaller particles show tangential accumulation. So it's different. And in particular, small particle is show unique properties. So after tangential accumulation, and the ellipsoidal particle is a little bit bending, like a banana shape, like this one. So this banana shape shows the fluid pressure is also contribute to this around the how to say chemical reaction, I think. And finally, let me summarize this information. So we estimate the temperature and the pressure around bubble by polyethylene beads behavior, and temperature around the bubble ranging from 70 to 100 degrees Celsius, and the temperature difference at the interface is 2 Kelvin. For anisotropic materials, EPBs, larger particles show radial orientation, and smaller particles show tangential orientations. In addition, we have obtained new findings. Sometimes the EPB was trapped at the stagnation point with rotating. So I would like to apply this phenomena to something in the future. So this research field started more than a decade ago. So other groups have reported excellent developments during this period. So one group showed bubble pen lithography, and another group printing. So there are more and more excellent review is recently we can obtain. And finally, let me summarize my talk. So I have talked about characterization and application of laser-induced microbubbles, and various phenomena have been found by cross-linking nanomaterials and bubbles. So we will continue to advance the fundamental understanding, so like fluidic manipulation, concentration, accumulation, chemical reaction, and and it's using this fundamental information to apply the orientation alignment technique and analysis method, crystallization, and patterning and manufacturing using the bubble and the nanomaterials. So that's all. Thank you very much for your attention. Thank you.
Thank you very much, Fujii. We're always fascinated to see the amazing science you can do at interfaces, especially when you can control and understand the underlying forces. We will have some questions at the end during the panel. So let's jump to our next speaker. And our next speaker is going to continue the story on bubbles. Professor Zhipeng Qin is going to be talking about to us about it takes 3 steps to Tai Chi, directly simulating microbubbles. And a little bit about our guest speaker here. He's an associate professor in the School of Mechanical Engineering in Guangxi University in China. He received his PhD in mechanical engineering from University of Maryland, College Park, in the US, under Amir Riaz. Then he moved from the East Coast to the West Coast, went to Stanford, where he worked with Professor Jenny Sukel in the Sigma Group from 2015 to 2018 as a postdoc. And then he jumped a few steps down the hall to Professor Hamdi's Chelepi's lab, also at Stanford, where he was a physical science research scientist. Then in 2021, he moved to Guangzhou University, where he leads a research group as a principal investigator. His research currently focuses on CFD, droplets, micromechanics, multi-phase flow, and porous media. Professor Qin?
Yeah, I'm here. So I can share my...
Go ahead.
So you can see my screen, right?
Go to slide view.
So could you have a look at that?
Yep, that's good.
Yeah, okay. Thank you very much. Thank you, Martin. And good evening, everyone. Maybe good morning for Martin. It's my pleasure to give a talk in this place. That is a very famous plane to discuss about our academic results. So after I heard the research of the Professor Fujii, I think, oh my God, it's a very amazing work, and we can totally see how the bubble moves. So that is the real world, actually. But in my research, I will give you another view to the motion of the microbubbles. That is from the CFD view. So from the CFD view, that is different from the real world. Is that it's discontinuity. We just to try to compute the governing equations for the velocity field and capture the interval. So here I give a name of my presentation. It takes 3 steps to Tai Chi. So Tai Chi is a very important part of Chinese culture. So that is similar to my work. Is that my model is also consistent of 3 important components. So combine these 3 components, I build a model to capture the motion of the micro bubbles. So actually, as mentioned by Professor Martin, I graduated from the University of Maryland and worked with Amir Riaz as a PhD. And Amir Riaz is a very famous guy in CFD, and he bring me to a new world about the CFD. And then, you know what? I go to Stanford and work in the volcano area. So that bubble is much bigger, than the micro bubbles. And then I also worked with Professor Hamdi, but Hamdi is try to capture the bubble motion in the oil recovery. So especially in the porous media. So in the porous media, the scale again reduced to several micrometers or nanometers. So actually, my model, I tested my models by the different applications. For example, the volcano, the big bubble, the video about several meters, to the bubbles in the porous media, which video is about just several millimeters or lower than millimeters and nanometers. So, to my understanding, what is the difference between the micro bubble and the macro bubble is that if we put a macro bubble with the video about several meters, it will, if we put it under the water, it will rising up and break up on the top surface of the water, for example, the lake. But if we put a micro bubble, it will not reach the top surface, and it will disappear and dissolve in the water. Why? Because that is too small. But some people found that under some special conditions, the microbubble will become a bulk nanobubble. And that bubble with a smaller size, but it can keep a longer life. So actually we have some questions, and that is also we are interested in is that how could we capture the motion of the bubble? And how and if the microbubbles deform or break out, for example, I see the videos given by Professor Fujii that they have some radio attack. In that process, how the bubble merge with each other and how the interface between the water and the gas deform. So that is the very interesting questions we want to ask and we want to know. So in order to solve these problems, we try to build a model. And the goal of our model is that we want to solve two problems. One is we want to capture the motion of the bubble. The second is that we want to capture the multi-phase interactions between the bubble and the bubble, or the bubble with the surrounding liquid. So that two goals are our main contribution we want to give to the other researchers. So that is we can also do the experiment, but you know what, the experiment is very expensive. Why? We need to spend lots of money to buy the equipment. And another thing that sometimes we cannot compute or actually solve out the force between the bubbles and the liquid and the bubble and the bubbles. So we want to use a CFD technique to do this thing. So what is the CFD technique? So simply to see that is that the CFD technique is try to discretize the multi-phase flow. I can give an example to you to show what is the difference between the experiment and the CFD technique. So in the experiment, it's just like the movie of Transformer. If you have a look of the transform process of the bumblebee, can I have a look of this video? It is very smooth, right? This process is very smooth, and just transform from a car to a soldier is very smooth, and it's continuous, just like a curve or a function. It's very perfect. So that is what we observe in the lab. But it's expensive. As I said, we need to spend lots of money on the equipment. So we want to try to reproduce the experiment by some code. By the CFD technique, we try to discretize this process to several segments. So just like the process the human build the finger. So when the people try to reproduce the transform process, they found that it is very difficult because the transformation, the bumblebee is made by God, right? It's not made by humans. So the people want to create something to fire against the bumblebee. The people want to use the human's way to finish this transformer process. So how did the people do that? We have a look of this video. Do you see that? The people have their own way. Is that the people led the car to discretize to some very small point at first. So that is the Lagrange point. And then let this Lagrange point to combine together to transform to a soldier. So in human transformation, they have 3 steps. First is the car transform to the point, to the Lagrange point. And then that the Lagrange point to transform to a soldier. So that is the difference between the Stinker and the bumblebee. That also be the difference between the CFD technique and the experiment. Okay, so but they have some challenges. As I said previously, the challenge of the experiment work is that it at first it is very expensive. The second is that sometimes it cannot find a good way to calculate the force between the different phases. but they also have some challenges to simulate a bubble. For example, if we want to simulate the motion of a bubble in the vortex flow field, for example, like that, we at least have 3 challenges. First, we want to capture the evolution of the phase interface. We can find that the interface is stretched to a long tail, and it deforms a lot. How could we accurately capture this process? That is the first challenge. The second is that because across the interface between the water and the gas, they have a huge pressure jump, especially for the microbubble, because in the microbubble, the curvature is very high. The curvature is very high, so the surface tension force is very high. So we have to engage this huge pressure jump across the interface. The third is that we also want to compute the velocity field of the multiphase, because we always want to solve the Navier-Stokes equation for the velocity field. But how to solve the Navier-Stokes equation, that complex equations, accurately and efficiently, that is always be the main point, the main question for every CFD guy. So the way I do that, I try to overcome these 3 challenges is use the idea of type. So actually, because in Chinese culture, we believe that the main important thing or the main important thing lays on the first step of everything. Because the people said that the word, all of our word derived from the initial, the one, the first one. So if we can combine 1, 2, 3 together, we can build a new word and we can solve the problem of the whole word. Okay, so I try to develop a new method for each of these challenges and then finally combine them together and to build a comprehensive model to capture the motion of the bubble. So let's have a look at the time loop of our model. So that is the overview of our model. So to capture the motion of the bubbles, we use this time loop. At first, initially, we give the initial value of the velocity, pressure, and the function phi into our model. The function phi represents the interface between the gas and the water. And when we do the calculation, we at first evolve the function phi. So that at this step, we use the level set method. And then we compute the curvature kappa around the interface. Why this kappa is important? Because this kappa is curvature, and curvature is a very important thing for the surface tension force across the interface. And then we give this computation of the kappa to the Poisson's equation of the pressure and calculate out the pressure. And finally, we give the pressure to the Navier-Stokes equation and sort out the velocity. And in the next time step, we use these velocities to move the level set function again. And by this loop, we solve the motion of the microbubble. But they have 3 very important steps. First is the level set method. How we represent the interface between the water and the gas. Second is that how could we engage the pressure jump into the Poisson's equation of the pressure. Second is that after we get the pressure, how could we solve out the velocity field? So currently, let me introduce the major steps one by one. Okay, at first, we use the level set function to represent the interface. How did it do that? Is that, for example, in this picture, you can find that we have several circles. That circles is the contours of the level set function phi. And we said the red circle, that is a 0 contour of the level set function. So we said when the phi is equal to 0, that is the interface. And when the phi is bigger than 0, that is the liquid domain. And when the phi is lower than 0, that is the gas domain. So by this way, we divide the gas from the surrounding liquid. And in order to move this interface, we just solve Hamilton-Jacobi equation. We solve, or we can call it advection equation. We solve this advection equation. You can see that is a V times kappa phase. So that by solving this equation, we can update the new location of the level set function, also the new location of the interface. But they have a question. If we only solve this Jacobi, the Hamilton-Jacobi equations, after several time steps later, the contours of the level set function will be disturbed, just like this picture. Why? That is because of accumulation of the error. So we don't want, the contours of the phase disturbed like that. Why? Because we want to calculate the curvature around the interface. So we need the value of phase around, the interface. But how could we solve this problem? How could we prevent the contours of the level set function from being disturbed? We need a reinitialization step. This step will help us to always keep the contours, the distribution of the contours of the level set function just like what it is at the beginning of the computation. So every time step, we solve the Hamilton-Jacobi equation at first, and then use a reinitializing step to redistance the function. How could we do that? We do it in 3 steps. First, we get the interface node at the interface. So that interface node is the intersection between the interface and the grid cell. You can find that the dashed line is the grid. We can get the intersections between the interface and the grid cell. So after we get the interface node, we will use some way to reconstruct the interface, like this smooth red curve. And then we project the value of the level set function to all grids, and then we can rebuild the contours of the level set function space, just like this. Always keep the contours to be not disturbed. But how we reconstruct the interface, that is the question. We have 3 ways. The first way is the point reconstruction. We just use the interface node to represent the interface. The second one is a little bit more complex. We connect the interface nodes one by one and use this segment to represent the interface. And the third one is the more complex one, but the most accurate one is that we use a polynomial to reproduce the curve of the interface. With each of this method, we will finally to find the lowest distance from the grid to the reconstructed interface, finally, and get the new value of the level set function at each grid. So by this way, we can reinitialize the level set function and give a very clean and smooth distribution of the contours of the interface. And in order to verify our method, we use a test case. In this test case, we initially set a circular bubble by defining the level set function to be a circular function. And then we give this bubble to our 2D vortex flow field. You can find that both of the u and the v is a function of time t. And the time t, when time t is equal to t, it's capital T, the u and the v reach maximum value, but when t is equal to 2 capital T, small t is equal to 2 capital T, the flow field will be recovered and the bubble will go back to its initial shape. Here we compare our simulation to others. We found that this is our the red one is our simulation. We can find that we get a very smooth interface, as well as the very clean contours of the level set function. But with other methods, you can find that the interface is broken out, and the conduit is disturbed. Because our final objective is to get the accurate computation of the curvature. So here we also do a convergence test for our computation of the curvature. We can find that our method can get the first order, which is better than other methods. We also show our conduit at t is equal to 2 capital T. Theoretically, the bubble at t is equal to 2 capital T, it will go back to its initial shape. So it should be a perfect circle. And we can find that the red one is our result. It realized that goal. But the blue circle is use other method. We can find that it's totally disturbed. So this test case can verify our method. The second one is that we try to engage the pressure jump into a Poisson equation. As we know that to calculate the pressure field, we need to solve the Poisson equation. But there exists some jump of the pressure across the interface. That jump is consisted of two parts. One is the surface tension, the second is the jump of the viscosity. That jump will lead a discontinuity solution of the Poisson equation at the interface. That is the interface. So because of this jump, we cannot simply combine the Poisson equation for the pressure in the gas and the pressure outside of the gas together. We should add something to represent the pressure jump. But how to add it? That is the question. So here we develop a semi-shock method. So this method can project the jump condition from the interface to the grid cell. For example, in 1D case, if we have a pressure P1 in the gas domain and a pressure P2 in the liquid domain, and at the interface, they have a jump in the P and a jump in the gradient of the P. So when we try to solve this equation, so Poisson equation, we have added a term, additional term in the right-hand side of the equation. And this W is a function of the jump of the P and the jump of the gradient of the P. And by this way, we can solve the Poisson equation with a jump condition with second order accuracy. For the 2D case, we do the similar things, but the difference is that we need to calculate the normal and the tangential directions at first, and then use that vector into the computation. And here we also use some test cases to verify our method. At first is the 2D case. We can find that the red one is our accurate. We can find that it can reach a second order. And we try to extend our method to 2D case. At first, we said the P2 is a constant value, the red circle. We can find that we also can get a second order, which is more accurate than other methods. And then we try to use a different shape of the interface. So in this picture, we use the shape as the elliptic interface. We can find that we also can get a second order accuracy. And finally, we use a triangle interface. It's a very strange interface. And we can also find that we can still get a high value as second order. So that proves that our SSM method can reach a very high value, which is at least one order more accurate than the current method. Finally, we want to combine our level set method and the SM method together to solve out the flow field. So we will solve the Navier-Stokes equation at first. And to solve the Navier-Stokes equation, we will solve an intermediate velocity at first, and then use these intermediate velocities to solve out the pressure. But in the step B, that is the Poisson equation, right? So here we need to use our SSM method to add the jump condition into this Poisson equation. How did we do? At first, for the microbubbles, because its curvature is very high, so the pressure jump is mainly caused by the surface tension force. So here I use a smooth profile for the viscosity. So I ignore the jump of the viscosity. only calculate the pressure jump because of the caused by the surface tension. And we use our SSM method to calculate the W. For example, if we want to calculate a pressure jump at the grid cell I plus 1J, we just use our SSM method and to use the to project the jump from the interfacial node Q to this grid cell, and then we can give this jump to to the Poisson's equation and solve out the Navier-Stokes equation. And here we use a resin bubble, the deformation of the resin bubble, to verify our method. We can find that with the time, the bubble will deform at first and finally break up. That is at a high Reynolds number about 100. So we can find that even though the bubble deform and break up, but it always keep a symmetric. And we also calculate the mass error. For example, in picture A, that is the mass error. The red one is our method. We can find that our method can always keep the mass error. I mean the mass error is the mass lost by the computational error. You can find that it always keep a very low value. So that means our method did a very good performance in the mass conservation. And we also compared our method to other methods. For example, we compare our method to the ghost fluid method. The blue one is ghost fluid method proposed by other guys. We can find that our method can not only to keep the error to a very low value, but it can reach a second order accuracy in the convergence test. After we verify our method, we use it to do some applications. At first, we use our method to capture the resin bubbles under the different non-dimensional numbers. So here in this picture, we show when we change the Reynolds numbers, EO numbers, or M numbers, and how the bubble deforms. We found that when the Reynolds number, because the Reynolds number is the radius between the viscous force, between the initial force and the viscous force, we can find that when the Reynolds number increases, the bubble will become more unstable, and it will become more easy to deform. And this is our simulations. We compare our simulations to experiments and get a very good accuracy. And secondly, we try to use our model to simulate the oscillation bubble. Initially, we stretch the bubble and then relax it. We found that the bubble will oscillate with the time. And in this process, the total energy of the bubble decays. And the blue line is an analytical solution about the energy decay proposed by Dr. Lett. And the red line is our computation result. We found that they can match with each other very well. The final application is the Rayleigh-Taylor instability. We use our method to capture the evolution of the interface between a heavier liquid and a light liquid. And we can find that it can capture the details happen around the interface. That is a very clean. You can see here, this is our simulation. Even though the interface disturbs a lot, it always keeps it as a symmetric shape. Okay, let me conclude our results. Actually, we built a very comprehensive model to simulate the motion of the microbubbles with an immiscible interface. And this model is consisted of 3 parts. One is the level set function. The second is the semi-sharp method to capture the jump. And third is a good Navier-Stokes solver. And our method can also use in the different scale, for the bubble in different scale. Okay, thank you very much. And if you have questions, you're welcome. You're very welcome to contact with me, and you can send an email to me or discuss with me by WeChat. Thank you very much.
Thank you very much, Professor Kim. Work and also a very, very good follow-up from our previous speaker. So I will move ahead and move to our final speaker. Our last speaker is Dr. Jiushuai Xu from TU in Germany. A little bit about our speaker. He's going to be talking to us about 3D microcantilever-based resonators for multifunctional sensing application. And our speaker today is currently working as a postdoc and serving as a junior group leader in the MEMS research team at TU Braunschweig. He received his PhD summa cum laude, that's the highest honor, at the Institute of Semiconductor Technology from the same university in Germany. Prior to that, he received a BS and MS from Northwest A&F University in China in 2011 and 2015, respectively. His research focuses on semiconductor micro and nano fabrication, advanced processing, MEMS sensors, and micro or nano detection system. He has published quite well, over 30 papers in academic journals and conferences, and he has also contributed in 3 books. So, Dr. Xu, please share your slides and take over.
Thank you, Professor Martin. So I need your help to confirm if my slides have been properly shared.
Yep, we can see them. Yeah, you're good.
Okay, thank you. Yeah, thank you. And also thanks to Professor Fujii and Professor Qin for their very nice talk, very impressive work on the microbubbles. So I'm going to talk about the microsystems where we use the 3-dimensional microcantilever-based resonators for multifunctional sensing applications. So first I will introduce the Braunschweig city. It's in the middle of northern Germany, 2 hours by car from Berlin and Hamburg, and it's a city of science of Germany 2007. So there are many research institutions and universities in this small city. Maybe this city is famous for another person, Kai Friedrich Gauss, who has been very known to the public because of this small story, the Gauss summations. He quickly figured out from 1 + 2 to 100 with his talent. So it's a very interesting and impressive story. So today I will start with another story because maybe most of the audience online will be the Chinese. So I will start from another story called Hao Chong Chengxiang. So it's also very famous and very smart kid. He solved the problem of the microwave, to separate the big target of an elephant to his weight to the equal weight of the stones. So use the boat as his balance. And today we are moving forward to the micro, to the macro, to the micro and nano world. And the hot topic of the MEMS sensors or the Internet of Things. There are many of the MEMS sensors for different applications to detect the audio, the IF communication, or smell, test, pressures. So today I will start a topic with the gas sensors. So the development of the environment or the gas sensors, the first reported gas sensors in history actually is the canary bird, where the miner took the canary bird to the mine to check the toxic gas. And if the bird is alive, that means it's safe for the people. And if the bird is dead, then of course it's not a friendly working condition. So nowadays we develop more and more microsensors. I will not introduce all of these words. It's boring to look at this, but we are aiming to the future smart sensors. maybe here we can summarize with two figures to help you understand better how those gas sensors or the environmental sensors applied in different fields. Like here on the left, in figure left, you can see on the environment monitoring, breath analysis, detection of explosive gases, so on. But currently, most of the semiconductor sensors or the metal oxide sensors, they have to deal with the high temperature conditions, or they have to use the detection and the reading out at the same same region. So will be a lot of challenges. And so today I'm talking if there's a possible sensing platform as a high performance gas sensors. So here I will introduce one of the simplest MEMS sensors, microcantilevers. It looks like exactly like the diving band with one end fixed to the silicon wafer or the bulk silicon, and it also works similar to the diving band. When it goes bending on the when it's moving to the resonanting, it can work as a mass sensitive sensor. Of course, for the microcantilever, it could be different shapes. But when it was working as the mass sensitive sensors, that means the mass deposit or attached on the cantilever, it could induce a corresponding resonant frequency change. By measuring this resonant frequency change, we can detect the adopted or the attached particles or the gas molecules, all of these nano size or the nanogram range detection targets. So I will not introduce or describe the detailed schedule of the equation. If you are interested, you can find it from the book. We described all of the mechanism and principle of the cantilevers. The cantilevers first reported by the engineer from IBM. So it is used as AFM to detect the surface profile or the surface microstructures. And as the sensor developing, there are microcantilever sensor arrays or for gas detection, or also the sensor have been specially functionalized for biosensors. And the main target is to functionalize or to decorate the microcantilever because the silicon itself is not chemical active. So there's some work to deposit 3D sensing materials to improve the sensing performance of the sensors. But the main idea is to decorate the sensor to build a 3D structure on the cantilever. So we were thinking, can we able to fabricate the cantilever itself directly as a 3D structure, or functionalize the structure to make it as a chemical sensor directly? And all of the process designed, we want it be seamless compatible, so it can be mass produced to reduce its price. So here I will introduce two microfabrication methods. One is known as silicon nanofabrication by the cryogenic deep reactive ion etching. The deep reactive ion etching is famous, known as the Bosch process. It has been used to fabricate micro or the nano silicon structures and for many years in industry. But it has also one very annoying problem, because during etching you have to switch the gas with some circles. Therefore, you will have some scalloped sidewalls. And this work I'm going to talk about is the deep reactive ion etching at cryogenic temperature. It uses different gases, and it can etch silicon nanostructure or microstructure with very small sidewalls. And here are some examples we did. You can play with this technique. You can make many interesting etching. You can etch the nanostructure perfectly with almost no damage to the structure itself or to the substrate. And what we have done is also we have employed many nano or microlithography technique to have different nano microstructures. Here are the examples. Is on the figure left, you can see that this method is wafer scale processing and very high aspect ratio structures as small as 15 nanometers. And it's unfortunately, I cannot introduce this work in very detail in this report because we just submitted all of this work and researchers to apply to the physics reviews, and we have been revising it for the resubmission. So I will cross my fingers. It could be accepted then maybe for the next time when we have a talk for the microfabrication or the micro machining, I can share this part of work. So here I will skip this work. And another method of knowing is a bottom up. Is where you deposit or you grow nanostructures on the substrate. We did also the area selective zinc oxide nanowires by the chemical bus separation and sputtering. You can control the wires very well in the defined patterns, and you can see the border here. And we can use this bottom-up technology as well as this top-down method to fabricate nanostructures. For example, here you have the Christmas tree-like nanostructures, and this is a combination of top-down and bottom-up. You will create some interesting 3D structures. But the question is how we create or microfabrication, these nanostructures on cantilevers, because the cantilever itself is also very small. It's only 100 micrometer in width. It's similar to the size of the hair. So here are also this interesting 3D nanostructure have been reported by some famous German media to give people warm greetings for the coming Christmas holiday. So here we come back to the micro sensors. We have to remember all of this fabrication happens on these very small micro cantilevers, and in our work we designed the cantilever also with the self-heating resistors. We use this one. You can just apply 5 volts to activate this sensor to resonate, so it can work as mass sensitive sensors. We use it as a portable environmental sensors, and we try to also explore its potential application as a highly sensitive sensing cause. And we also try to use it for the contact resonance images to check their multifunctional applications. First, I will start with the portable environmental sensors. Remember, still again, all of this process we did from the wafer to the device, final device, or by ourselves in our lab. So the first application is for the particular matters, which known as the PM 2.5. There are many aerosols and particles in the air. So some of our colleagues have done very excellent work before to use the particle sensors. Here on this figure, you can see there are some particles adopted on the cantilevers, so they can check the resonance frequency change, the resonance frequency curve change, and also the resonance frequency change according to the particles. And here the sensor is not really functionalized. The particles are adopted by an additional magnified magnetic field, and we are trying to functionalize it for the application. First, we did the application for the humidity or the moisture detection, because the humidity detection also have many applications in different fields, especially for the respiration and respiration monitoring. For the indoor humidity, it's easy now with many sensors you can do it. But for the respiration detection, you need a very high sensitive, the very high performance sensing platform. So here is how the sensor have been fabricated. And you start with the bulk silicon and fabricate the cantilever, try to functionalize with the different structures here. For the humidity sensing, we functional the cantilever with a nanothin structure. And you hear the xenoside nanoparticles have been selectively deposited on the cantilever as a sensing film. I will not introduce the whole process in detail. If you are interested, you can find the paper, or you can write to me. We can also talk in detail. Here are the some figure of merits of these sensors and also dimensions. And we compared our sensor with one commercial state-of-the-art commercial sensors. Here, the red curves are the sensors, capacitive commercial sensor, which cost 400 euros. And here you can see clearly our sensor has a better performance at the high humidity range, because the high humidity range is always challenging for the humidity sensors. And since it has very good performance, we are trying to use it for some respiration detection, which you can see. You can detect the breath not only from 10 centimeter, even much further 6 centimeter. You can have very clear signal as well. Here are the short video. Here you can see how your breath influence the sensor output, and how the sensor responds to the breath, to the different distance and different humidity. And it's interesting to know all of these figures. Like also here, you could find that the respiration before and after spot. If the respiration is normal, you have around 20 times every minutes breath, and the signal is also pretty even. And if you do some sports, the breath is much sharper and much fast. You will have 36 or 40 times breath every minute. If you compare, this signal is also clearly to modify some respiration change, and the sensor has very fast response and recover. And also you will find that interesting if we actually evaporating moisture or the humidity all the time to the environment. If we measure our finger, you can see a clearly response because of the moisture evaporation. But if we put on the wrapping glove, you will see that the signal maybe mostly induced by heating, by temperature, is very small. And it's also funny that this moisture evaporation is pretty constant. If you wash your hand just after washing, the moisture evaporation signal is pretty huge, but as time goes, it goes to stable. Actually, it could also be like one signal for the body health or for the body states. And furtherly, we did the detection with some portable device to check its response. Of course, because the sampling frequency of this portable device is pretty low, so we have to play this video with 4 times speed. You can see here the signal change, because the finger is not contact with the sensor is there around 5 centimeter distance. You can still have the signal and pretty fast, very good repeat signal. And after this, we found okay, it's good as a portable sensor, but it's very sensitive. It's very sensitive. Maybe for many, like the portable detection, they don't need so high sensitivity. And we are checking, looking forward to see if it could be even higher sensitivity as the sensing profile for some large instrument. Here, you can see here the diving gold medal winner of the Tokyo Olympic Games. similar to the diving game, it's the same. For the sensor, you need not only very sensitive, but you have to be selective. Only selected moves you can have a higher score. For the gas sensor, same. Only selected targets or the gas should be detected and selected. Here also the process how the sensor have been developed from silicon wafer to the final sensor, and here are some SEM structures. You can see how the silicon wires and zinc oxide wire on the silicon wires, and all of these structures actually on the cantilever. Like if you still remember this sensor on the finger, all of these structure we made also on the cantilever. So for the mass sensitive sensor, as we mentioned before, it's interesting because we don't need too high temperature to make it work. We can combine with a micro LED. So when the sensor is with a certain wavelength light illumination, the certain gas like here NO2 can be adopted. And then when we change the light condition, then the gas can disrupt from the sensor, so you could have the clearly signal how the sensor responds to the different concentration of the gas, and it could reach the limit of detection of 2.1 ppb means part per billion volume. So it's very, very sensitive. And if we compare if the sensors have been only simply modified by some chemicals or with one-dimensional modification and a three-dimensional modification, you can see clearly the sensing improvement by the 3D structure, by the super high surface area is about 600 times improvement. And if we measure the sensor at different time with different conditions, we found that for the 31 days, it's very stable signals can be still found. And as these two presenters before today, they did also very impressive work when to introduce the Microbubbles. We did also some try of this application of these sensors in micro liquid. So the sensor have been machined with this micro fins as for the humidity sensing, and the micro liquid can goes through here, the microfilms, and the adoption can happen. And we made some 3D printed assembler, which you can put the sensor inside, and the whole device size is like 1 euro coins. And if we combine this device to the flow rate controller and also some output regulation, we can find that the sensor is also very sensitive and very high sensitive to the microfluidic, to the microflow change. And this is also interesting and funny since most of cantilevers, they are not able to work in the liquid because the damping of the liquid is pretty large, and the sensor is not able to work in liquid online. And by give it some 3D structure and in-plane resonating, we can use also the microcantilever in liquid, and this work is in process for publication as well. So the last work is similar to the AFM. We worked with one of our PhD students to develop a setup here. The cantilever used as the sensor to detect the microstructures, for example, to detect the large-scale micro and nanowires. The advantage of this setup is that you can use it to sweep very fast compared to AFM, and you don't need very large instrument, very accurate light source. You can still detect the micro wires to generate some 3D structures. And here are the example here. For example, you have the wires of 4 micrometer height, and diameter 1.2 micron pitch 4 micrometer. With this setup, you can depict the micro topography of the wires. And here I come to the conclusion. I hope I convinced you that these self-sensing, self-actuating microcantilevers, especially their 3D structures, can use as the portable environmental sensors and as highly sensitive sensing cores, as well as working in the surface and contact resonance frequency imaging. And thanks to all of my students and also, of course, Professor Evan Piner giving me the opportunity to co-supervising and coordinating this MEMS group to do some interesting work. Thank you all.
Thank you very much, Dr. Shko. We really appreciate that amazing work on sensor development. So we will switch to our panel now. And let me, our first panelist is Alice. Alice needs no introduction. Is the founder of ICANX and a very well-established professor in the flexible electronics world. Then we have with us Professor Xiaoming Xiang, who is joining us from Optics and Thermal Radiation Research Center, Institute on Frontier and Interdisciplinary Science from Shandong University in China. A brief about our panelists. He got in 2019 from School of Aerospace Engineering in Tsinghua University in Beijing. He did research with Dr. Xiang about the use of laser-induced bubble dynamics. And then he moved to Dr. Dieter Ohl's group at Otto von Guericke-Magdeburg University in Germany. He also studied at exchange PhD student in Professor Muller's group at LWTH University, where his research focused on the numerics of fluid structure interaction. After graduation, Dr. Xiang joined Professor Pei Zong's group as a postdoc at Duke University, our neighbor here. And in April 2023, he joined Shandong as a Qilu Yang Scholar, and is also appointed as a faculty in the School of Energy and Power Engineering. Welcome, everybody.
Thank you.
Now to our panel. I give, you go first.
Okay, it's very my honor to be here to ask questions. It's very excited to listen to all the three lecturers here. I learned a lot from their talks. So I have some questions here first. So first is Professor Fujii. So I'm very excited to listen to your fascinating talk. So I have three questions related to your talk. So did your bubble oscillate or will disappear when you fire your laser? And the other question is related to the details of the laser. What's the post profile of your laser? And you said that you just say the power of your laser, but didn't mention the energy and or the post duration of your laser. And the other is in page 17. I saw the ring structure, but you say that this ring structure is like accumulation of the particles. Did you like say the cavitation, because you have laser-induced cavitation? So the cavitation erosion is a very important phenomenon related to this kind of laser-induced cavitation bubbles. And overall, I think for the laser-induced cavitation bubble.
One by one, okay? Tell me
okay,
by one.
Okay.
Otherwise, remind how many questions you ask.
Okay, that's very basic questions related to your experiments.
Thank you for giving me the questions. And the first question is about oscillation.
Yeah, did you observe the bubble oscillation, or your bubble will disappear when you fire your laser?
Yes. So when I am doing my experiment, so the laser, bubble oscillation is observed when laser keeping irradiation. So if laser,
so you use continuous laser?
Yes, continuous laser. Yes.
Okay, I got it.
And just laser turn off, the bubble quickly disappeared. So in the decreasing process, we have no oscillation observed.
Yeah, it's similar to oscillating boiling.
Yes.
Yeah.
So that boiling is a keep irradiation.
Okay, I see. Yeah.
Yes. And
then is the overall physical, the physics behind your experiment. Because for the laser-induced cavitation bubble, it have, I think, may have two effects. One is the photoacoustic or photomechanical effects. The other thing is the photothermal effect. But I didn't observe any, like, you didn't discuss the photothermal effect. Does laser-induced heating will affect like your DNA manipulation or chemical reaction? Did you discuss this in your study?
Yes, thank you. It's a good question. So I think photothermal effect is a dominant factor compared to the photo interaction. So because the laser trapping system, the laser trapping the interaction distance is very very short.
Okay.
In contrast, in my experiment system, the interaction length is quite far. So more than 20 micrometers. So that means that the photothermal effect is a dominant factor, I think.
So it means that the total energy deposit in the liquid is too small to heat the fluid.
Total energy?
Yeah, because you find your air power is not very high, and the total energy deposit into the liquid is not that high enough to increase the temperature.
Yes.
I see. Okay.
Yes.
Okay. Yeah. The last question is, I observed this very interesting ring structure in slide 17.
Yes, a Prussian blue structure.
It's ring structure, micro ring, right?
Micro ring, yes.
Yeah, it's for from the view of cavitation bubble dynamics. When the bubble collapses, it will also induce very like form a ring structure, and then it will form the ring damage from our study. So I'm thinking, is there anything related to this cavitation erosion? Because you just say that the particles accumulate around this ring position. But I think maybe some micro ring damage there, and then those particles accumulate stays there.
Yes. It's also a good question. The first of all, so this accumulation process is very quick, and and after laser irradiation off, and the cavitation bubble and shrink and disappear, and after the event, so we measure the micro spectroscopy, and so each particle is no damage.
Oh, good. Oh, I see. It's very interesting experiment. Yeah, thank you very much.
Yeah, thank you.
Very fascinating to talk.
Yeah.
Okay. Yeah. So then I move to the second speaker, Professor Qin. Yes, I also did some numericals before, but it's compressible multiphase flow. But when I listened to your talk, so it's very impressive that you did a lot of work solving many problems we haven't solved before. Yeah, so it's very interesting. So then my question is, because you just talk about you first talk about the nanobubbles, and then you use the Navier-Stokes equation to solve the bubbles, right? But there are some scale effects for real nanobubbles. So may have, because why the bubble can persist in bulk fluid for several hours or several days.
Yeah. So actually, you mean the time scale, right?
Yeah, the time scale.
actually, the bubble. Actually, you know, the original objective of this model is try to capture the macro bubble. Just for example,
it's macro bubble.
Or macro bubbles. But for the micro bubbles, actually, in the macro bubbles, the time scale is very low. It's just several seconds. For example, several seconds or several meters. Miniature. But I think for the small bubbles, it will be the time scale will be long, as you said, right? And but you know, for the small bubbles, the model will become more efficient, because for small bubbles it will be not easy to break up. It's not easy to deform. So it will help us to save the time. So I think that the model can work more efficiently than the macro bubble. But for the macro bubble, it always break up. And when the bubble break up, at some especially region, the maximum velocity will become very, very high. And you know that if the velocity will become very high, that means we need the lower time scale, the time step, very lower dt. But you know, when the bubble can always be, you know, keep on deformed, you know, the dt can be much higher than the macro bubble, so that model will become more efficient. I think it can solve the it can solve the problem in several hours.
Okay, so the real physics is very complicated. Like for the nanobubbles, they may have mass transfer, or like even phase transition can occur, and also like for in real conditions, because the water is not pure, we have impurities. So I'm wondering if your code can extend, you can just like upgrade your code to simulate real problems, like include mass transfer, or like bubble particle interaction, or or your code can like include any like the scale effect from the micro to macro scale. It's very interesting to see this.
Yeah, that is a very, very good question. So actually, I also do that, you know, at the same time, as you said that you also do a simulation for the compressible case.
Yes.
And you know, I also switch out my model from the incompressible to compressible. I can just what I need to do is to change the continual equation and add the term about the changing of the density. Okay, and I can and our model can also, you know, combined with the thermal equation and the mass transfer equation. We can just you know, add some, for example, the equations for the volume fraction or something, or we can add additional term to the continual equation. That should be okay. And we, you know what, we also capture we also add the particles, the solid particles to our computation.
If there are particles, very interesting.
Yeah, because you know what, previously I used my model to simulate the multi-phase flow in volcano. In the volcanoes, we have all the solid, the particles, crystals.
Yeah, bunch of particles there. Yes. They have different sizes.
Yeah, different size and different scale.
Yeah. Okay. So it's very interesting to see this. Then if you like later, if you can like upgrade your code to incompressible, like then you can, because now in your code the bubble always persists there, because they only have deformation. If some bubbles may appear or disappear, so that's also very interesting. Like the laser-induced bubble, like Professor Fujii, he did some like experiments, because they create a bubble, then later very quickly the bubble disappear. If you can like simulate this process, they're also very interesting. I can like work together with Professor Fujii to explain their phenomenon. So it's very interesting.
So it should be very.
Yeah, very fantastic work. Yeah, and that's. Thank you very much. So that's my question for you. So then for the third speaker, Professor Xu. So I'm not an expert on this part, but as I only have two questions. One is because I'm not in this field, so I want to know the working principle. You mentioned that you can fabricate different geometry configuration. So it means that if you can detect different gas species, so it only depends on the structure or geometry or structure of the this microsensor. And how about, did you change the material of your 3D cantilever?
Okay, so actually the geometry of the cantilever mostly decides is a physical property. So for the detection of the gases, like I mentioned, we have to do some functionalization for this cantilever. Of course, in the idea of we proposed, we want to make the cantilever itself also 3D dimension. Then you can easily to integrate with some semiconductor technologies, for example, sputtering or other common technique. This technique mostly they are film technique. They will give you materials only film. But if you make the platform 3D, then the deposit film will be also 3D. So your sensor performance will be improved.
I see. So it's very interesting to see this kind of sensor. Yeah, I think this is very useful in the future if you can put into industry. You can, yeah.
Yeah. This is also the idea of this work. Actually, if we see the sensors now actually applied in our real life, actually they are mostly the physical sensors with very small geometries or the small design. If it is too complicated, and if it will be not able to make it application. Of course, for the sensor, if we apply with some 3D synthesis materials or the 2D materials, it will have very obviously improved performance, but how to make them mass production to make like the microphones you have every year billions sensors have to be produced. For those materials, it's not possible. It's very difficult. So this is the idea behind this work.
Yeah. So in the future, if you want to sell your your sensor, so what's the what is the price you give to the to the old or normal people?
Yeah, that will be my final target of my dream to do so. Still a very, very long way, I think.
I think it's possible in the future. Yeah.
Yeah, thank you.
Yeah. Very nice talk. Yeah, it's very interesting to see all this. Thank you very much.
Alice.
Yeah, I'm here. Okay. Yeah, so Gaoming is really a great panelist, Yeah, I'm great you have many questions and really in the field. So I'm not in the Bible field, so yeah, I have some questions for Jiushuai. Yeah, Jiushuai, you have demonstrated that sensors. You mentioned that it worked in the liquid very good, right? Yeah.
Yes,
So,
yes.
yeah. So I mean, if we're working in the liquid, normally you should consider of the dumpling. Yeah. So
Yes, yes.
yeah, the liquid, the with the allergy or something.
Yeah.
So how did you consider this?
Yeah, maybe I don't have time to explain so detailed before, but for the most cantilever, if it's to the out plane, we call like out plane resonanting. So if it's resonanting direction is perpendicular to the liquid, so the damping is very serious. And in this design, we make the cantilever like in plane resonanting. The resonanting direction is same as the liquid, or like in the liquid. So the only is sidewall against to the fluidic when it's resonanting. So the damping has been reduced much more than like outplane resonanting. And like we did also the microsense like through like small channels on the cantilever, so it can increase the contact phase of the cantilever and the sensing target, but again reduced the sidewall area to reduce the damping more. For this cantilever, mostly like you mentioned before, the outplane resonant cantilever, it will have the Q factor in liquid maybe only 10 or 15. It's very difficult to use them for application. But for this in-plane resonant with 3D structure, we found a Q factor of 120 for the completely immersed in liquid.
Okay, that's really great. That's why a lot of people, they really work on the sensors. It's now working liquid, kind
Yeah,
of
we are also
environment is
just
really
started
hard.
to move to the liquid. So it's many challenges. Maybe also questions for these microbubble experts because they want to create bubbles, but I hate bubbles because I'm amateur now to the microfluidic. I hate bubbles when I want to build some microsystem. The bubble will destroy the signal. So maybe you have idea also how to destroy to eliminate these bubbles in micro liquid.
Yes, really great. Actually, yeah, for Fujii, you are working in the microbubbles is really really nice work. Now Zhipeng was working for the simulation, right? The theoretical. So looks like you guys can calibrate a little bit. But I have a question is like Gaomin already asked, how you consider about that in your simulation or in experiment too. But the most important thing is the temperature. Normally, for these bubbles, a little, change of the temperature, it may affect a lot, right? Yeah. So, but how you consider of the, this kind of environmental and the parameters, especially for this temperature of the pressures. So, how do you put in your theoretical study? That
Yeah,
critical one?
yeah, that is a very good question. The temperature is also is indeed very very important. And but currently I did not consider the temperature into the effect of the temperature to the motion of the micro bubble. But I consider the temperature on the macro bubble when I use my model to simulate the motion of the bubble in the volcano. Because the people believe that why the volcano can erupt is because of the bubble. Because the bubble moved from the tip of the earth to the top, it will bring the heat to the conduit of the volcano. And in this process, the bubble will bring the fresh and hot magma from the tip of the earth to the top of the conduit, and at the same time bring the cold magma and the dead magma to falling down to the deep of the earth and reheat again. So actually, previously I combined the continual equation and the momental equation and the thermal equation together to solve out what the motion of the bubble, how the motion of the bubble affects the temperature field. And but for the volcanoes, the viscosity of the magma is very sensitive to temperature. When the temperature decreases just several degrees centigrade, the viscosity will increase several orders of the magnitude. So the viscosity is the connection between the temperature field and the velocity. But I currently I did not consider too much about how I connect the momental equation and the energy equation in the micro bubbles. Maybe Fujii can give me some hints. Yeah,
Yeah,
and later on
Fuji's
I can add.
exactly.
Yeah.
Yeah. And thank you, assistant. And I need your help. and, so to understand microbubble. So also I obtained the streamline and the laser local heating, but the obtained data is removed. How to say multi-physics. So just obtain the streamline. So I want to understand the next step is collaborate with the temperature gradient and so. But this calculation is very difficult, so that's why I need your help.
Yeah, we need help with each other. Yeah.
And maybe if I can jump here and say that's one of the biggest pride point of ICANX. We bring people together and then we create connections where they often don't seem to exist, or you're in the same field, but you don't know you need each other.
Yeah.
So we are very happy to hear this conversation. Alice, can I jump in here?
Sure,
okay.
please.
Yeah. So actually, in that conversation about temperature and viscosity, Zhipeng, you showed how you used the Navier-Stokes equation to kind of build your solution to the model that you have. as a surface scientist, when you talk about a bubble, I want to pay attention to the surface, to the edge of that bubble. And if you look at the molecules in the bubble, they are not in the same thermodynamic state as the bulk of the solution. And because of that, there's going to be a divergence in viscosity as you move from the bubble into the bulk.
Yeah.
How do you factor that in a turbulence Leno's average Navier-Stokes equation in finding your solution? Or did you think about that?
Oh, sorry, I did not think about that too much.
Okay.
Yeah, and actually that is the work I'm doing right now. Just I answer the questions to Gaoming is that currently I think that it may be because currently I try to modify my model to consider how to the bubble disappeared and appear and arise in the bulk. You know, I try to modify my model. For example, maybe I can add a compressibility to that, and by this way I can to simulate the disappearing process of the bubbles or the extension of the bubbles, and also I can add a mass transfer equation to the continuum equation. Maybe add an additional term to the right hand side of the continuum equation, and maybe use that to change the densities of the gas area, maybe something like that. So that is my work in the future. Yeah, that's a good question.
Actually, I would even suggest that maybe you should think about how you look at surface tension gradient at the interface, because I've seen, especially when you have mixed materials, the interface of that material is not homogeneous. It has a gradient. It's a tensor. It actually builds a stress. So if you consider that as a stress that is decaying as you get into the bulk of the material, then when you're thinking about compressibility, then you realize that it's not a simple strain propagation. You don't focus on stress propagation. You actually look at strain propagation, and you treat it as a soft deformable colloid, right? Then that way your tensor becomes a perturbation to the strain propagation across that interface before you get to the yield. A lot of people look at it from a stress propagation, and I don't think it's correct.
So I think so. You suggest me to add the jump of the stress at my model, right? And because when the bubble compressed or extends, it have a stress jumped across.
Yeah, there's a gradient from the edge of the bubble going to the bulk of the liquid.
Yeah.
This interface here is not smooth.
Yeah.
It's not an instant. It's organized. Those molecules do organize themselves, and they cause speciation. And actually, we have captured that in phase transformation. I think Gaoming asked you about phase transformation, and we have captured that very well in phase transformation of materials. It forces materials not to freeze for extended periods of time. Interesting discussion. I would ask you to look into it.
Sure.
It's very complicated process.
Yeah.
But it's beautiful though. It's really beautiful. Don't let it go. It's like a beautiful space.
Yes.
Right?
Martin, maybe I can share, my bubble to everyone. Have a big surprise, okay?
Go for it.
Oh.
Please see my bubble.
Oh, there you go.
Wow.
Yeah, great. Actually, this is a real bubble. Yeah, I made it. Yeah. So thank you very much for the nice job.
So a quick question for you in terms of in your description of the slight temperature gradient and the ensuing Malagoni flow, how do you couple that to the no-slip boundary condition on the gold surface? Because if your DNA is sitting on the surface, it's sitting on a place where the liquid is not moving, no matter how much Marangoni is going on here. So is the straightening of the DNA being driven by the shear force of the Marangoni flow? Or is it driven by basically adjacent Marangoni flow? Because then at that point, the Marangoni flow will be tangential. Is it driven by that shear, or is it actually being pulled by Marangoni convective current?
Yeah, so in now I think there's only Marangoni flow, and so in my bubble, so driving force, 3D mechanics driving force is a surface tension gradient, and so surface tension gradient provided the Marangoni flow and the Marangoni flow, and each point of the velocity is different. So the different velocity is creates a shear force, and so then the DNA is extended.
Okay, I'm looking forward to a lot of discussion on that next week. So can we?
Yeah, welcome.
So it's gonna be very good.
Okay, let's enjoy.
Yeah, very good. And then, Joy, so quick question for you. You showed very interesting smooth fabrication. Have you thought about the role of self-assembly in making your materials instead of using subtractive manufacturing? You use self-organizing systems to build the structures you want. That way you can make them even at a single molecule. And we talked about Chris pre the talk. Chris Nighthouse, he's doing amazing work with single molecules. And at University of Twente, is that a path that you see some of these sensors going so that you can put more probes on your cantilever? Or is it too difficult for you at this point?
It's a very good point. And so previously I tried and self-assembled monolayer surface, and then there's a irradiation and then making bubble, and then after making bubble and scanning and the substrate surface, I checked the FM and no topological changes of the, but the Kelvin force microscopy, so surface potential is different. So that means some chemical reaction is occurred, but I don't know the details, but it's difficult, but very interesting.
Very good.
Let's discuss next week.
Yeah, we can talk about it next week.
Yes.
Can I ask the same question to Dr. Chu? Have you thought about self-assembly in making your sensors?
Yes, please.
So the question is, you're making very small sensors, right? Have you thought about using self-assembly?
Yeah.
So that you can make the sensor smaller, or you can increase the number of sensors you have?
Yeah, sure. Like actually, for one of the.
Go ahead.
Sorry, maybe the internet doesn't work so well. Could you repeat?
I'm saying, have you thought about using self-assembly to organize very small features on your cantilever instead of etching?
Yes, actually we did. We did also some self-assembly work to functionalize or to modify this cantilever with some very small molecules or the groups, functional groups. This will improve the property of the cantilever. Actually, we can combine even like the 3D substrate and also the self-assembly. Actually, we are doing this. It's very interesting also.
Very, very good.
Thank you for your very good idea and suggestion.
Yeah, no problem. Actually, with that, allow me actually to bring us to a conclusion, because we are 2 minutes away from 9. And so I would like to thank all of you for attending and present these wonderful certificates to you. If this was a live conference, we would walk on the stage and hand you this beautiful certificate, Professor Fujii. But now please accept the virtual presentation. Same with Professor King and Professor Zhu. Please accept our virtual certificates, and thank you so much for gracing us with your wonderful work. And with that, I also want to announce next week's talks. Please join us. We'll be having some very interesting work on advanced manufacturing with fibers, with presentations all from the US. Kinan Song and Kevin Fu and Wubin Chang will be presenting. And I also want to remind everyone about the upcoming ICANX Davos Summit, July next year. And very special and dear to me and to this forum is a Young Scientist Award. We ask all of you speakers and everybody who's listening online who is eligible. If you got your PhD after 1st January 2014, you're welcome to apply. Please send us your documents and we'll be very happy to consider you and hopefully to reward you for the amazing work you're doing. And with that, I want to say thank you very much and have a wonderful day or evening.
Okay,
thanks,
great.
everyone.
Yeah.
Yeah.
Yeah,
that was-
cool.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。能够像我一样飞越最高山岗。
祝你生日快乐！该吹蜡烛了，来。